Otherwise, I think it was her first day on the job.
Okay.
How's that for yours?
Yeah. And your life.
Recording has
I'm
started.
doing 50% of web, then doing rapid, which is a mission. Challenging is F mission, fast mission. So we started not even 1 year ago. We want to launch 2030. Yeah, and doing liaison scientist for Roman.
Put 28 up there. There's 2 minutes and then just as much or a little of your time as you want. And then we'll, Cosmic Dawn Center, is that where Jacobson is?
Yeah, Peter.
That was going to be my question actually. Do you see him at all ever? Still cranking with it. It's almost like watching on a virtual meeting too. You just wait till the flow trickles down and all right, everybody, let's do this afternoon session. Thank you for coming back on time. We can circulate microphones if you guys need them in the audience. Yeah. Okay, good. Now I think we're all here. Good. So, Gabe, please proceed.
Thank you. Yeah, and thanks for the invitation, Marco and Jeff. It's great to be back to see you all. Yeah, I was invited to talk about wide field slit spectroscopy with JWST. I must admit that with all the excitement of all the, with so many different instruments and modes, this might actually be the thing I've been looking at least. The spectra and the NIRCam images have been so exciting. But I think there's still a lot to be, there's really a lot of exciting potential with this mode here. Even with a true spectrograph, with NIRSpec, there's still a very interesting niche that wide field slitless spectroscopy can do with James Webb. And it's already proving to be extremely powerful. And I'll show you some of our experience on some of the collaborations I've been working on. And I won't give a full review of all some of the science results and things, of course, but some sort of technical issues here. So just to set up why this is a compelling and I think complementary mode with the imaging, NIRCam imaging that we heard a lot about in the first couple sessions. We'll hear, I think, a lot more about both NIRCam and also NIRSpec. But wide field slitless kind of sits in between those modes, right? So here on the left is an image. This is an image of a lensing cluster from the Canucks GTO survey led by Chris Willett. So we have you've got the images of this cluster field, and then you put in this the imaging, the GRISM element there, and of course that disperses the light of it's just. Shall I wait a second? chance if I...
And the cursor, move it.
No, the screen's okay. As long as I can go back, but I can't go back and forth. Now oh, it's on the screen there too, so we kind of want to get that.
Cursor too.
Hey, somebody's wondering, JWST makes this noise.
There it is there.
So we'll work it out.
Thank you, Thomas. Okay, so of course, taking a step back here, we've got the image on the left. This is, in this case, it's a NIRIS image, but it's very similar to the NIRCam images we've heard this morning about. But on the right, if you rotate the filter wheel and you put in the dispersing element, this grism, you get spectra of everything in the field of view, and that's why I think it's a complementary mode, again, in between those two that still has a niche to fill here with JWST. So you can see features like these big kind of hot dog looking things are the continuum spectra of these bright cluster galaxies. But then you see the other, the kind of smaller concentrated things, those are emission lines. And at the top there, that's an emission line of 0.3 at a redshift of, I don't know, maybe 2 or 3 or so. So you get a spectrum of everything in the field of view without having to pre-select targets for slits, without requiring that things fit within, or are well-centered within MSA slitlets, any of that. So in terms of completeness, it has and multiplexing, that's really the main benefit that wide-field slitless provides. And also some spatially resolved information potential in the lines I'll show a little bit about. But then, that benefits also then that doesn't come for free. It's a challenging mode to process the data, and I'll show some of the considerations for NIRIS and NIRCam are a little bit different for the slitless. But so our approach from the past couple of years with Hubble and in the past has been that we really try to model the full field of view here, where you model the spectra of all these overlapping sources. You can then calculate, everything overlaps on everything else, and so to extract a clean spectrum of a particular source, you need to remove all of the contaminants. And so that's where the real challenge lies that you need to overcome before you can realize those benefits. Okay, so here's just a quick summary of the wide field slitless modes for James Webb. So you've got the NIRIS with the broadband filters from 1 to 2 microns. And then you've got also in NIRCam in the long wavelength channel now. You can cross all of the broad and the wide and medium filters with 2 grisms in the 2 different NIRCam channels. And that's been particularly exciting. As you can see in the figure below, the line species that you see in the different grisms, the red here are NIRIS, where you get H alpha and F200 out to redshift of 2. But in the NIRCam grism, you get H alpha out to redshift 6.5 or so, O3 out to redshift 7.5 or 8. So we've seen with near spec, of course, that these spectacular high equivalent width emission lines we know, and I think that's been somewhat even of a surprise with this first year of James Webb, how really strong emission lines some of these early galaxies have. And NIRCam provides a way of getting that at these redshifts of cosmic dawn. Okay. And so this is the one kind of workflow slide of how I, in these collaborations, have been processing the data, and I'll go through some of these steps here, but then for the rest of the talk, I'll be more showing kind of what some of the capabilities are, and at the end, mentioning some of the analysis challenges. sort of following the model of some of the earlier talks, I'll just mention, specifically the processing steps that we do where you go from querying the archive to process data. So if you'd want to try the code here, I'm happy to help people if they want to experiment with it while I'm here. It's now pip installable thanks to James Davies and Eva, so that's really been really helpful. And so the workflow here is kind of built on a lot of the expertise and history that we had with Hubble and now porting it to James Webb. So I define my own custom associations. They're very similar to the associations we heard about earlier from Howard and others, but maybe basically just associating any exposure that was taken essentially with a single guide star acquisition. That might be a little bit different than the official definition. If sometimes APT, you might kind of split up different exposures into different sort of subgroups. And so I do use the level 1 processing to do the ramp fits, and I start with the rate products. I do my own 1/f masking, very similar to what we've heard from Ryan and the other talks this morning, and also the snowball masking like James mentioned earlier. I should say that for the flat field calibration, I apply the imaging flat to the wide field slitless exposures under the assumption that it's kind of the wavelength dependence of the pixel sensitivity and things is more or less reproduced by the imaging flat itself, and then that's much easier to determine than to determine it separately for the wide field slitless, the grisms themselves. I do my own astrometric alignment where what my goal is to be able to process and align JWST exposures with exactly the same code and the same software that was done with HST. And so to do that, I need to basically take out the JWCS model that we heard about this morning, and I use the SIP approximation to that, which has worked quite well so far. And I do my own alignment to some reference catalog, generally Gaia if possible, but a lot of these high latitude survey fields don't have, we talked about, Armin talked about what happens when you get down to 8 or 10 Gaia stars. A lot of these fields have 0 Gaia stars per pointing. So you need some other reference that might be Hubble, in some cases Hubble images. There's a master sky subtraction step for the slitless, and right now I'm just using the master skies that have been tabulated by Nora Perskow, which I think are even from pre-launch data, but that gets us pretty close, and I'll show a little bit of that. And then the next step is kind of one of the more computationally intensive steps, at least for NIRISS, where you are NIRISS, where you're calculating this full contamination model. You know where the sources are because you make a source catalog and detection image, and you can make this contamination model for NIRISS. That takes some time, but you can start by just doing that once, and then perhaps refine that based on your, you can then do the extractions and fit redshifts and templates and things, and then refine that. Right now we're just doing like a one-pass contamination model. For NIRCam, I'll show in a minute, we do a little bit differently, with this method that was proposed by the GTO teams. And then so that you have to do kind of just once for a particular program or a survey field. You process all the data, you do the alignment, you've got the exposure files, and then you can just store those. I do all this on Amazon Web Services, so that's all stored on Amazon S3. And then from that, you can you can then extract individual spectra, which involves making a catalog, making little 2D cutouts of every spectrum from every exposure that contains a particular source. Then you can model the redshifts and fit emission lines and things like that. Okay. So happily to talk about details of that throughout the week. So here's again this NIRISS image of one of these lensing clusters. This is with one of these the bluer blocking filter, F115W. But you can also, you step through F150W, you see they kind of shift from left to right as you are selecting a different part of the spectrum. Now you've got those emission lines that pop in, and F200 you get different lines. Or sorry, that should say F200. Okay, and so one of the, I think, real strengths of this is getting 2D emission line maps, and this is something that we spent a long time developing with the Hubble grisms, Wide Field Camera 3 in particular, and the 3D HST survey. And the way that we do this is actually kind of treating them almost like the dispersed images like images, like normal images, in that you you can make effectively a narrowband image at any wavelength you like by essentially just kind of shifting along the trace of a particular spectrum and then just kind of pretending like the image was an imaging image, okay? And this little picture shows how that looks. Like if I kind of drizzle this 2D map on the sky at different central wavelengths, you kind of see that, at 9,000 angstroms, these things don't quite line up. But when you kind of get the redshift right or the wavelength right of this feature, whoops, it kind of stops, and I meant to stop it there. It doesn't stop, but there's one wavelength which corresponds to the observed frame wavelength of that line, where everything kind of lines up spatially on the sky from these different exposures that had different position angles of the prisms. So you can make these 2D line maps in essentially the same pixel frame, like undistorted, rectified frames that you have in the images. Okay. And so here's an example of this. This is from a paper from Jasleen Matharu, who's part of the Canucks and also the NGD teams that we heard a little bit about. So these are just an example of these, a particular example of some of these strong emission line maps from the nearest spectra, that you get all these different line species and you've got these 2D maps. So it's almost, you can think of it as, it's not exactly an IFU cube, right? Because with nearest, the spectral resolution is really low. They're spectrally unresolved, but they are spatially resolved with the spatial resolution of JWST, which is, of course, exquisite. Okay, and so, and as we move out to higher and higher redshifts, so we've been doing this for years with Hubble, but measuring these Lyman breaks and Lyman alpha emission lines at cosmic dawn type redshifts was always just kind of out of reach, because either it was just at the sensitivity limit, and where you become really sensitive to your ability to model all this contamination. Here's a simulation of this redshift 11 galaxy GNZ11 that I did in 2017 or so. And now actually with NIRISS and the Canucks program, this is this MAX 1149 JD redshift 9.1 source, where it almost looks identical to that simulation there. So we can now measure Lyman breaks with the slitless spectroscopy. Of course, you can also do that with near-spec spectra as well. Okay, so now to move on a little bit from NIRISS, which, NIRISS you can kind of think about as just like a really powerful Hubble WFC3 GRISM that goes a little bit redder. But the near-cam GRISM is kind of really a different beast than what we're used to looking at least from the Hubble days. So here's what a dispersed image now looks like in the near-cam F444 filter from this FRESCO survey led by Pascal Usch. And so, the immediate thing to notice is that these spectra are much longer. They take up a lot more space on the detector. And that's because both, the bandpass is broad, but also these are very, quite high resolution dispersing elements compared to what we've been used to with Hubble. This is R of about 1500. Okay. And so, immediately if you looked at this image, and when we were kind of making these plans, kind of a little bit afraid of how sensitive we would be to our ability to model the contamination, because these spectra are so long, and in principle the contamination is really high of a particular source. But the Eiger GTO team, which I'm not involved with, but collaborate with Yorat Mate, for example, they came up with this beautiful approach that has become extremely powerful for the near-cam GRISM, where you say, okay, well, I don't actually really care about the continuum. What I really care about is emission lines. And so if that's the case, the instruments were well built and well characterized. The spectra are more or less parallel to rows of the detector or columns. And so what they proposed, and what works actually really well, is you just take a median filter along the dispersion direction of the image, with a large filter size, maybe 70 pixels, and you can subtract that, and really just without doing any modeling at all, you just subtract out the contamination more or less instantly. Okay, so there's some residuals that come out, some self-subtraction of the lines themselves, and maybe some ways to improve that. But it really provides a nice way to get to emission lines in the near-cam GRISMs really quickly without having to worry about this modeling. And also it means that you're not nearly as sensitive to the actual details of the precise calibration of the traces in the GRISMs and things. And we heard a little bit about alignment from Ben and others, where you can easily measure shifts of 1/10 of a pixel just if you're taking difference images in that of images. The same is true of the grisms. If your calibration of the dispersed traces is off by 1/10 or 2/10 of a pixel, that shows up instantly as residuals in your contamination model that are kind of limit your ability to particularly extract continuum spectra of faint sources. So if we apply that to the fresco image here, we can subtract out all that contamination, and these two particular things are, I think it's bracket alpha at redshift like 0, essentially, these beautiful line maps. But all these other little things are Paschen alpha and O3 and H alpha at much higher redshifts. So that's what we've done for fresco so far, and that's what the GTO teams have been doing. And so the motivation for this was that work with Hubble and IRAC from Spitzer, in the last decade, suggested that at these cosmic dawn redshifts greater than 6 or 7, the IRAC photometry itself suggested that there should be really strong emission lines, just because the IRAC colors suggested that there were strong lines there. Here's an example from Renska-Smit in 2015, where you see this strong excess of the IRAC channel 1 filter that was indicative of a strong O3 line. And then, we simulated what this might look like back at this JWST community day that I gave a talk, some of these same slides, 5 or 6 years ago. This is what we thought a spectrum might look like. Okay, and now the GTO team, Fengwu Sun and Nor Perskal and others, found some of these high equivalent width lines in the very first dispersed near-cam grism spectra that were taken. This is a calibration program. So immediately, I think, was already very promising. And now here's the fresco spectrum of exactly the same galaxy from Renska-Smit's paper, where in fact you do see that here's this high equivalent width O3 line here, measured with very high precision from the fresco spectra at a redshift of 6.9, which fits right in the middle of where the photometric redshift from Renska's work was. Okay. So now I'll go into a couple points here, kind of outstanding issues, I guess, that are in some cases limiting our ability to kind of really dig as deep as we'd like to go into these images and really push them. So here's an example of modeling the full field, in this case, the F200W filter for nearest from the CanNux survey. And so if we make this model, it looks a little worse than it actually is. But you see there's these slight offsets that, maybe it's the wavelength calibration, maybe it's the sensitivity calibration, maybe it's both. If you just shift these just a little bit, then they just don't quite line up. And that might not matter for a particular source so much, but what you care about is, really removing this source so that you can get at the faint one underneath there. And that's why you need the calibration to be as precise as possible. Also, you see there's kind of a systematic residual of these zeroth order spectra, particularly in the F200 filter, where the zeroth orders are quite bright. If those don't line up perfectly, then it becomes hard to mask them, for example. You might not care. You might just say, okay, if I think there's a zeroth order there, I would just mask it and ignore it. But if it's not quite at the right position, then even the masking is not going to work very well. So we've been working on trying to modify that, the trace calibration a little bit, and that is working a little bit. But this is kind of limiting our ability to really push into the nearest spectra. And I should say that it's particularly hard in these CanNux fields where there's a big bright lensing cluster right in the middle of the field, which has all these bright cluster galaxies. So that's kind of the worst possible case that it could be in terms of the contamination. But that's where there's still some room for improvement, improving the trace calibration and also potentially the sensitivity calibration of nearest. Okay. Another calibration challenge, at least that I think is solved now, but I'll mention it here, is the near-cam wavelength calibration of these high dispersion near-cam grisms. So what we notice is that you can get kind of a totally external measurement or estimate of the wavelength calibration, not from a standard wavelength source or whatever. But if you look in these survey fields, in this case, the fresco fields, where you have all these spectroscopic redshifts that you measure from the ground with MOSFire or whatever, you can then measure those same galaxies, the redshifts with the near-cam grism. And if the redshifts are different, that systematic difference could potentially be some imperfection in the wavelength solution. And so what we found with this version 4 version of the calibration, which is the version that Nor had made before launch, that it looked pretty good in the A module, but in the B module, there was this measurable offset of maybe 200 or 300 kilometers per second that was kind of shifted now. And this is, just with galaxy spectra and redshifts here. And what we found was, in fact, that the calibrator that had been used for that is this planetary nebula in the LMC, and where the calibration spectrum hadn't included the radial velocity offset of about 200 kilometers per second that had been measured for that source previously. And so that we could measure, and NOR implemented that, and that's now corrected. And just as a little side note, this offset, systematic offset at the very high redshifts in module A, where it looks like the NIRCam redshifts are systematically low, that's not a calibration offset, that's actually astrophysical. And the cause of that is that those tend to be galaxies, redshift 5, in the ultra deep field where the redshifts come from MUs. So the redshift is Lyman alpha, where the GRISM redshift here is H alpha. And so that offset is actually a velocity offset between Lyman alpha and H alpha, which is astrophysically interesting. Okay, and so to blink these, the systematics are now basically gone as of the 1123 map, so that's solved. This I just came across in the last week, and I thought it might be particularly interesting here, not just for the GRISMs, but also for the people doing imaging, is looking at the sensitivity calibration of the GRISMs. And so there's a very nice suite of data of the white dwarf calibrator P33OE from Carl's calibration program. And what these figures are showing are the observed spectra in, these are both in module A, GRISM C, GRISM R. Oh, I'm sorry, yeah. They can see me on the screen. I can't see the cursor, actually. Well, I won't point at it. I'll just try to explain it then. But so the top is just the observed spectrum. The middle is, if you divide out by the shape of the spectrum, and you see that absorption line there is actually a real absorption feature in this white dwarf. But then the bottom curves are then what I infer as the sensitivity curve for this particular filter. This is the F410M filter. And what you see is, and the yellow curve there is what's currently in the CRDS, the reference file, the sensitivity curve. And not only is it offset in terms of the overall sensitivity by maybe 10%, that's within the stated uncertainties, but actually you can use these data to measure basically the shape of the filter curves, and the shape is actually a little bit different. And it's subtle, but as we start to look at median surveys with these median bands looking for emission lines and things, you can actually see that the wavelength cutoff there is, as derived from the GRISM, is actually quite different than that inferred in the pipeline. I think that's also the one that's used in things like Pangaea and others. And you can do that for both GRISMs and also both modules. And you see maybe the shift in the actually edges of the filters is not quite as bad in the B module, but it's still significant, and we can measure that with the GRISM. And then here's the full white dwarf spectrum, which I think is quite beautiful with this is the 4 micron spectrum of this white dwarf standard, just to show what it looks like with all these absorption features there. So I think this is just a first glimpse at using these data to improve the calibrations, but I think we'll be able to improve those significantly. Oh, I'm sorry, solar analog, P3G. I guess that's all the absorption stuff, I guess. Yeah, that's not a white dwarf. Yeah, sorry, thanks, Paul. One last point here, which I think is actually, it's both a headache, but also I think pretty exciting, is that at this high spectral resolution, the NIRCam wide field spectroscopy is spectrally resolved at scales that galaxies have kinematics of order of hundreds, few hundred kilometers per second. That's the spectral resolution of the GRISMs. And so that does complicate our ability. What we've done with Hubble in the past is you just assume that your line is unresolved, so you can make like a narrowband, effectively a narrowband image in the emission line. But that no longer works for NIRCam because the lines are distorted by the kinematics. So if I blink back and forth here, you can see, okay, this is the image itself, and then the next panel are the Paschen alpha lines at redshift of about 1. And if, with Hubble, like they would just kind of lie on top of each other, and the differences you would interpret as differences, for example, in the H alpha spatial morphology versus the continuum. But here, the differences are not just in the line emitting region, but also in kinematics. So in the left one, what you see as I keep going back and forth is it's kind of squished. And it depends kind of in a complicated way that it depends which side of the galaxy is, coming towards you versus going away from you, and also which way the dispersion goes. So if it's, if the dispersion is one axis, it's squished. If you rotate 180 degrees, it'll actually be spread out, extended in the opposite direction. And actually using that, you can, I think, break that degeneracy. But in the rightmost panel, you can actually see what turns out to be kind of a beautiful little rotation curve in the Paschen alpha line at redshift 1.4. So this is almost like a little position velocity diagram, again, with very high multiplexing. You can do this with the near-spec IFU, but you can do this for many galaxies at a time with the wide-field slitless. And so at the very highest redshifts, there's now even been a couple of papers on this, one from Fresco, from Erica Nelson, where we've got, she's measured a rotation curve in H alpha at redshift 5.3 with the Fresco spectra, and now a potentializing one and potentially very interesting from this MAGNIF survey, which is a cycle 2 program. This is a paper by Lee et al., which that proposes a kind of rotation curve in O3 measured from the grisms here. But to do this requires, some pretty detailed sort of full modeling of the spectra. It's not a trivial measurement. Okay, and the last thing I want to mention, the challenge here, is just distributing, these data products. We're here talking about what, data products and how we use these data. I mean, some of this is just because this is a spectroscopic data set and that there's just like a lot more dimensions to that problem than there is to, say, a photometric catalog. But it's also that wide-field slitless spectroscopy is kind of a friends of friends problem. You got things contaminate others, and here everybody's friends, or at least they know each other, and you have to keep track of all that as you are doing the analysis, but also potentially, trying to interpret catalogs and things. And also, I think, as I've tried to show a little bit, that you have to generally kind of do all this modeling in the full kind of 2D space of the dispersed images, because the shape of the spectrum, it depends on the morphology of the source. So you have to kind of keep track of all this information, and that just is hard to kind of a different way of distributing things than, say, catalogs or images. The way that we do this now is just with some kind of crude databases and web tables and things. But I think where we'd like to go with this, I just wanted to end with here, is this is a map viewer that I've been developing for the images, but potentially with the slitless spectroscopy that you could imagine kind of seeing the overall context of where a particular source and images are. So this is the good south field. I'm just zooming around in the map here, recenter on a position, and then I'll turn on a layer that shows you both near-spec spectra and the Fresco prism spectra. And so you can actually get a kind of a more, I think a contextual sense for a particular source and what its neighbors are like. And so there's some O3 lines popping up. That's the near-cam grism, and that's now a prism spectrum from near-spec. So that kind of thing, I think, these types of tools, I think, will be necessary and helpful for interpreting this tricky data set. And then I'll just end here with I'll just leave this up as I maybe entertain some questions just to advertise this effort that we're calling the DJ, the Don JWST archive, where we've processed a lot of imaging data and now some of the slitless optimized, in this case, for kind of high latitude extragalactic survey fields, a lot like what Nathan was talking about this morning. We've got our own versions of a lot of mosaics. There's also a database sitting behind this that you can query for footprints and overlaps and all this kind of stuff, and I think that becomes really powerful as we want to try to use all of this data set. You can see your favorite survey there, but you can start to treat this as one very large survey that's really powerful for, in this case, distant galaxies. So I'll stop there.
Thanks, Gabe. The next two talks are remote, yeah. So while we're setting that up, I'll entertain the audience with a couple of questions here. Sure. Marco, you can set that up. Grab a mic. How do you set up your association files?
Oh, I query masked with the Astro Query interface, and then I calculate my own overlaps. And I mean, I have my own database where I call them associations, but it's basically starting with the masked query, use the footprints that tell me how things overlap in the program IDs and things, and then calculate the associations that way.
So all automated.
Yeah, pretty much.
Okay. And then I guess some of the dispersed spectra that continue could have absorption lines in them. Is that a concern at all?
Yeah, a little bit. I mean, at least for the near-cam spectra at 4 microns, the spectra are pretty featureless, you know, at most redshifts out there. You do see some residuals. You didn't see them in the figure that I showed, but for example, there's these CO bandheads at 2 microns. So at redshift 1, you kind of see this ringing and things that sometimes from the contamination, but in general, you don't see that. If you were interested in extracting, you know, the full continuum spectra, you would have to do things more like the modeling way that I said. You wouldn't want to filter it all out first. So we haven't really explored that too much yet.
Yeah, and then I think there's a question that says, to what extent can this be? Can you automate your stuff versus having, or if somebody wanted to use it, can they just use it out of the box, or does it require some, you know, tuning by hand kind of stuff?
Pretty much out of the box. I mean, the associations that I've defined, like you can query those, and I mean you can, like the pipeline is kind of built to use those, but you can query those yourself. And like, I mean, if it's a particular program that I haven't ingested, you can ask me, but I've ingested pretty much everything. I haven't processed everything. But that we can talk about maybe later this week. And I mean, the documentation, such as it is, it's not you know, a full documentation suite. There is at least a bit of some minor test suite. But the documentation is basically some notebooks that show, okay, if I had this pointing in the UDF or maybe NG deep, if I wanted to process that, there's some notebooks that show how to do that.
Perfect. Thank you so much. We will have a wide field spectroscopy session day 3 and 4. If you're interested, contact me.
Hello, can you hear me?
Yes, we can hear you.
Yep, you can see my slide?
Yes, we see your slides.
Okay, thank you. Can I start?
Yeah, go ahead.
Okay, so hello everybody. My name is Gabriel Oliveira. I'm a PhD student at Federal University of Santa Maria in Brazil. And in this presentation, I'm gonna show you how to solve a problem that you possibly have to deal with if your observations were made using near MRIs. Our team proposed observations of 3 nearby AGN host galaxies, promising hosts of strong molecular outflows, to spatially resolve the molecular gas kinematics and understand how the winds driven by the AGNs interacts with the gas in the context of galaxy evolution. To our surprise, all of the targets came with these flickerings. This one here. I hope you can see my pointer. These flickerings are high-value pixels, visible both in detector images as well as in the final data cubes, and are not removed using the pipeline standard outlier detection. As you can see, in the image detector, the flickerings have 2 main patterns, the cross-shaped one, this one here, and the single pixel one, this one here. These artifacts are dispersed all over the detector image, both in spatial and wavelength axes. So, the main concern associated with this kind of outliers is that they make it difficult to identify structures in the target, even more so if the object is being observed for the first time in the infrared. Another concern is that the values of these pixels match the values in the high signal-to-noise regions. So it's very difficult to visually identify where in the continuum or in the emission lines these flickerings are located. Also, in the final data cubes, they don't show up as a narrow spike in the spectra, so you can't apply traditional cosmic ray removal algorithms. So how do we detect these flickerings? We utilize different kernels to compare the signal of the flickerings to its surroundings, using the cosmic ray flagged files. The CRFs were a good choice because a large portion of the outliers are correctly removed by the pipeline. Then we just need to deal with the ones that are left, but they are a lot, so we have to deal with. For the single pixel pattern, we compare its signal to the 8 surround pixels. For the cross-like pattern, we consider as the signal the median value of the 4 cross pixels, this one here, and we compare it to the 12 pixels around it, the pixels around here without the X. The bigger the difference between the pixel and its surroundings, more likely it is that we have an outlier. We also consider the median absolute deviation of the surrounding pixels in the detection. The idea is if you have surrounding pixels with near the same value with a bigger difference in signal, you detect an outlier. If the surrounding pixels have random values like this one here, even if you have a big difference in signal, you don't detect the flickering. So this approach works fine, but it excludes way more pixels than necessary, so we implement other two kernels, the vertical and the horizontal one, these two guys here, to detect continuum and emission line and separate the high signal from the low signal regions. Finally, the majority of the cross-like flickerings have the central pixel, this black pixel here, have the central pixel with nonlinear ramps in the uncalled files. So we look for the ramps with the highest last values, fit a power law function, and identify the ones with nonlinear behavior, flagging them. So after all, after the detection, we update the data quality map, the third stage of the pipeline again. And here is some of the results. For the sake of better visualization, I add 2 more slides just doing the zoom on these results here. Here are the results. I hope you can see the pixels shifting here in the screen. And finally, the script takes around 2 and 50 seconds to run in 1 jitter image using 1 thread of an Intel Core i7 laptop. This is the final result for the cube, so we remove all the artifacts. Thank you.
Thank you. Perfect timing. So Marco's going to bring up the next.
No, it's Tim Brandt.
Tim
Yes.
is just going to present. Yeah.
Yes, we got to.
Got it.
Okay,
Tim, can you
if
take
this
over?
works.
Yeah, perfect.
Does this work?
Yeah.
Okay. Let me see if I can do. Oh boy. Inconvenient. Let's see. So I'm going to talk about something that hasn't come up yet today, telegraph pixels. It's a little bit of a niche application, but potentially interesting to some of you, especially if you care about recovering some pixels that are currently masked. Depends on your science case. A telegraph pixel is something where the reads look like this. This is a case where the difference in telegraph levels is fairly large. So you see what looks like a nice ramp, but then there's this jumping. So this is a 2-level system that can be in either state A or state B. And depending on whether it's state A or state B, you jump around. If you have an ordinary least squares model, that's not going to be a great way of fitting this. So right now, the pipeline just rejects these pixels. It's of order 1% of the pixels, so it's not a huge fraction, but it's a significant fraction of the bad pixels. So one thing that you could do is to change your model from just a simple least squares to something that accounts for the fact that there are these 2 levels. So we can do that with the Gaussian mixture model. The math isn't too complicated. It's on the poster. The implementation is a little bit more of a work in progress because it's no longer a linear least squares problem. It's not something that you can just minimize and get deterministically. You need some kind of an iterative approach. So it doesn't play as nicely with the kinds of algorithms you would want to build your ramp, but it is something that can salvage these pixels. So in this case, if you just do a least squares fit, you would get that orange line, which is pretty bad. If you just use the first 10 reads, those ones that are colored in dark blue, and you use this mixture model, then you do way better. If you look at a large sample of pixels, then as long as we have at least, let's say, 6 individually saved reads. So if you're averaging your reads into groups, this works much less well. But if you have the individual reads, then you can almost fully recover the telegraph pixels with this approach. So depending on your science case, a significant fraction of the bad pixels may be recoverable if you have a decent number of reads and if they're individually saved, as in 1 read per group. Feel free to look at the poster if you're interested, and I'll be talking more about ramps tomorrow. Thank you.
Excellent, thank you. So now we have some in-person poster presentations, is that right? I see, okay, well, we can come back. Thomas? Yeah. So Marco, do you think it's possible Maria will show up before the end of the day?
I'll try to contact her soon.
Okay. Well, we will find a spot if she shows up.
Is the mic working fine in the room?
Check if it's red or green.
It is red.
Oh. What about now? Yes, okay, I can hear it. Cool. Right. So hi everyone, I'm Thomas. I'm a PhD student from Montreal working with René Doyon and Loïc Albert, who's here this week. This work is also in very close collaboration. It's actually mostly led by Jens Kammerer, who was a postdoc here and is now working at ESO, and also Rachel Cooper and Anand Sivaramakrishnan here also at Space Telescope Institute. So I'll present the kernel phase pipeline for high contrast imaging below the diffraction limit with JWST. Now, just for a bit of context, what I work on is imaging exoplanets and brown dwarfs with JWST. Now, the directly imaged exoplanet population is a very small subset of the total known exoplanet population. It's at the top right here of the plot, basically, so the most massive and further out planets in their systems. And James Webb will help us to detect more of these planets in 2 ways. First, with coronagraphy, we should reach much lower contrasts than we've been able to before. And then, to reach closer separation, we can use interferometry with James Webb. And there's only one Webb telescope, unfortunately. So the way this works to do interferometry with a single telescope is we use aperture masking interferometry. Aperture masking interferometry means you put a small mask like this in the pupil plane of your telescope, and your PSF becomes an interferogram. So like we see here at the bottom. When this happens, we're able to derive quantities called closure phase, which are used a lot in radio and optical interferometry. And these quantities are basically robust against phase errors in the atmosphere, or in this case, in your instrument. And this enables us to reach high contrast at very short separations below the diffraction limit and much below the inner working angle of coronagraphs on Webb. This is great, but there's one big caveat, which is the throughput. Because when you put this mask in the path of light, you lose about 15%. You get only about 15% throughput. So we can't do this with very faint sources. This works around bright stars, but not other targets. If we want to extend similar capabilities to faint sources, we need something that really exploits the full mirror of Webb, and that's what kernel phase interferometry does. Kernel phase basically turns Webb into an interferometer, but keeping all of the light that comes in. And the way we do this is basically we take a regular image, but we treat it as the result of an interferometer. Basically, we describe the mirror of Webb as many, many small sub-apertures or sort of sub-telescopes which all interfere together and give you the image at the end. Now, if we do a bit of math, I'll just have a few slides to explain how this works. Consider on the left you have your telescope, and each of the small points in my model of the pupil of the telescope has a phase aberration like this. If the phase errors are small enough, you can actually describe the resulting phase errors in the image by a linear equation, this A matrix here. Transfer errors from the pupil to the image. Now, if there's an object that we're observing, so for example, a companion, then the phase signature that we get in the Fourier transform of our PSF is described by the phases of the object. So the Fourier transform of an object in the sky translates directly into the Fourier transform of the image you observe. However, you also have to add in small phase errors coming from the telescope. So if we can have a way to remove this term on the right, we just have a direct mapping from whatever image we're observing to the Fourier transform of our image. And we can actually do this. We just have to find a matrix that when we multiply the whole equation by it, removes the A term on the right. That matrix is called the kernel of the matrix A, hence the name kernel phase interferometry. And when we do that, this K times phi here, which we call kernel phase, gives us a quantity that is free from errors on the telescope and basically just relates to the geometry of the object, of the scene that we're observing. And we can leverage that to detect companions at very short separations around faint objects. This only works if the wavefront error is small, so if you have a high Strel ratio, which is the case with Webb, so we don't have to worry too much about that. Webb is actually the ideal observatory to do kernel phase. But despite that, it's not an official mode for Webb. So when we do kernel phase with Webb, it's just a regular imaging observation that we schedule, and then the pipeline treats it as a regular imaging observation. So if we want to do kernel phase, we have to write our own tools to do it. So there's no official pipeline, but we have tools that have been used with HST and with ground-based instruments that were converted to work on Webb. And even very soon in the existence of JWST, there was kernel phase planned. So even during commissioning, because kernel phase leverages many concepts that are very close to aperture masking, so you take a Fourier transform of the image you get, and you work with phases and many techniques that are inspired from long baseline interferometry, kernel phase observations were scheduled during aperture masking commissioning. So we observed 4K giant stars to test kernel phase and make sure that everything was working according to plan. And there were several GEO and GTO programs that were using kernel phase with NIRISS, NIRCam, and MIRI to search for companions around brown dwarfs and white dwarf as well in the case of MIRI. So all of this led to the development of a dedicated pipeline using tools from HST and from ground-based telescope. And this was led by Jens Kammerer, so the pipeline is on GitHub, here you can find it. And it's inspired by the main Webb pipeline. So it really mimics the whole structure of the JWST pipeline, which makes it very simple to use if people want to test it. Can I click on this? Yeah, okay. Yeah, so the way it works is we start with a 2D image or 3D cube. We crop it, recenter it, because we really want to focus on the star of interest where we're looking for a companion. And we recenter it properly to make sure that there's no artifact, because we're going to take a Fourier transform of this image and we don't want any effects to appear. The bad pixel correction in the pipeline is a custom one, because when you take a Fourier transform of your image, you can't just ignore the bad pixels, and you need to correct them very well, otherwise it gets very messy very quickly. So what happens is, if you take a Fourier transform of an image with bad pixel, you get very clear signals that you're not expecting, like that the geometry of your telescope doesn't allow. So by identifying these signals and removing them, we're able to very precisely correct for bad pixels, even if they're close to the PSF core. So that's very important when we're searching for companions that are 1 or 2 pixels away from the primary, to properly correct bad pixels even close to the main star. Then we do a super Gaussian windowing just to make sure that there's no edge effects when we take the Fourier transform. And then we extract kernel phases. That's the core of the pipeline that does most of the work. So up to here, we're working with a regular image. Here we take a Fourier transform, extract kernel phases with the K matrix I was talking about earlier. Then we estimate correlated noise in the data. and we produce what's called a KP fits file, which is basically a regular fits file with extra headers and extensions defined to sort of standardize this type of data, the same way that OI fits data standardizes interferometry data. Yeah, so this is what the pipeline does, basically. It takes the image with the Gaussian window on it. We define a pupil model like this to treat web as an interferometer. We take a Fourier transform, and then we measure the phase. And what I'm showing here at the top left is every point here is a sample that we have of the phase based on this model. And everything outside here that looks very messy, that's what we're unable. That's basically too high of a spatial frequency. So web is not accessing those frequencies. That's too long outside of what web can attain. We need a bigger telescope to go reach these points. So we really want to make sure that none of our red points is in there, because then we're just getting a lot of noise in the data, which is not the case here. You can see that the phase